Hello, this is quick pre-calculus review for calculus, part 21. It's also part 7 of the second unit, which has these topics that you see right here. In part 7 of unit 2, we're finally getting to talking about the very special irrational number e, special in math just like pi is special. If you've taken pre-calculus before, you should have seen it before, and hopefully you saw it in the context of the compound interest formula, because it comes up in a very natural way, and that's one of the main reasons I'm talking about the compound interest formula in Unit 2, though it's got nice applications as well. Also in Part 7 of Unit 2, we're going to think of the complex interest formula in its most natural form as an exponential function of time, and as we often do, we'll use manipulate in Mathematica to animate the graph with p, r, and n as animation parameters, meaning think of this as a function of t for fixed p, r, and n. However, different values of p, r, and n will give us different graphs, and we can see how the values of p, r, and n affect the graphs. We have really a family of functions here. Initially, we thought of this as defining a function of p, where r, n, and t were fixed, so that was a direct proportionality. Its graph was a straight line through the origin. Then, by letting b equal to 1 plus r over n to the n power, and representing the function this way, we ended up thinking of b as being the variable, and p and t as fixed. It was 1000 b to the 10th. That was a power function of b. Now again, in the most natural way to think about it, we'll think of the exponent t as being the variable, p and b as being fixed. Equivalently, p, r, and n as being fixed, and think of this as an exponential function of t. But we'll start by going ahead and thinking about the number e by looking at example 2.3 from the last video, where we found and compared what's called the annual percentage yield, or APY, for two accounts. That's a number that basically gives you the actual annual percentage growth. That's what it's defined to be, and it gives you a method of comparison. Whichever bank has the better APY is going to be the better bank, as long as the fees are the same otherwise. Since B represented the annual growth factor, if B was, I think we got 1.077 in an example a few videos ago, that was a number you multiplied by your balance by at any moment in time to find the balance 1 year later. Annual growth factor multiplied by b. That means that if you subtract 1 from it to get, in that case, 0.077, 7.7%, that will be the actual annual percent growth. So the APY is b minus 1. Since b is 1 plus r over n to the n power, here's the formula for the APY. We use Mathematica to find its values, and in both cases, for both Bank A and Bank B, we got values of the APY that was a little bit bigger than the quoted nominal annual interest rate R. The 8.5% compounded biweekly ended up having an APY of 8.86%, and the 8.4% compounded daily, essentially, the banker's year with n equal to 360, gave an APY of 8.76%. So Bank A was better, but we also did see that if we reduced the R to 8.41%, that Bank B ended up being better. So it's not just the interest rate, it is also the number of compounding periods, but the interest rate has sort of a bigger effect on the APY than the N does. We made graphs of this expression for the APY as functions of R. Notice I'm letting R go from 0 to 1 here. The axes are going to be labeled R and APY, and I added this feature that you see right here, aspect ratio automatic, that makes the scales on the axes the same. You get a graph that looks like this. This is the case where n is 1. In the case where n is 1, you see a straight line. In fact, it is the 45-degree line when the axes are the same scale. APY equals r when n is 1. But once n becomes bigger than 1, like 2, then the graph becomes concave up. The slope of this graph gets higher and higher as r continues to increase, which means for fixed delta r, for fixed change in r, the change in the APY will be bigger if r starts out at a bigger value than if it starts out at a smaller value. As you continue to increase n, you see the graph, in a sense, gets more and more concave up, but the effect gets smaller and smaller. When n is very large, if it increases by 1, say, it does technically change the graph, but by such a small amount that you can't see it. We also thought about this thing as a function of n. Let me put a minus 1 in here. And change this to an 8/100ths. We thought about this expression for the APY as a function of n. We took the r to be 8%. I typed it in as an 8 over 100 instead of 0.08 because that allowed us to use the capital N command in Mathematica to get the value of the APY to 20 decimal places. You also, of course, could reduce the fraction to 2/25. And we can see the value of n. When n is 1, it's 8%. That's the APY. This is the APY here. When n is 2, then the APY becomes bigger than 8%, 8.16%. When n is 3, it's 8.215% approximately. As n continues to get bigger and bigger, the APY continues to get bigger and bigger as well, though the effect is small. In a sense, it's diminishing returns. If you were going to graph the APY as a function of n, evidently it would be increasing but concave down, although it wouldn't be a curve, it would be a bunch of dots since n is a discrete value here. It's not that you can't plug in fractional values of n into the formula, but the way we think about it with the application, n has a discrete value. It's a whole number, a positive integer. All right, so that's what we're going to experiment right now, and this is what we're about to do new. Let's experiment with this. Let's imagine a great bank account that's got 100% interest rate. So R is 100% or 1 into the formula. What will happen in that case? Well, when n is 1, if you compound once a year, the APY is also 1, 100%. Your money is going to double. Think about that. If you had 100% growth, you put $100 in there, after 1 year it's going to double to $200. The growth is 100%. If n is 2, what's going to happen? Why don't you think about that for a second with me here. If n is 2 and it's 100% interest rate compounded twice a year, that means each 6-month period your money is going to grow by 50%. If you put $100 in there, that means after 6 months it's going to go to $150. And after 6 more months it's going to grow by 50% again. 50% of 150 is 75. 150 plus 75 is 225. So your money more than doubles. It grows by 125%. Let's see if that happens here. Yes, when n is 2, the APY is 125%. You could continue experimenting, for example, when n is 4 and confirm that the APY would be about 1.4414, 144.14%, etc. Once again, as n increases, the value of the APY increases, but the returns, the rate of return in a sense, is lower and lower. It doesn't seem like it's maybe going to get past 1.72. Now, if you remember the number e, you might remember the number e is about 2.718. This looks like maybe it might be e minus 1. In fact, let's get rid of the minus 1 here, which is why I didn't have the minus 1 there to begin with. What happens now if I get rid of that minus 1 and let n increase? This looks like it's getting closer and closer to the number e. Amazing. This is a limiting process that's getting closer and closer to the number e. Yes, that is the number e, closer and closer. In Mathematica, you can enter e in two ways. You can either use a capital E to represent the number e. There's the first 100 decimal places of e. Let's see, 1,000. You can memorize that if you want. Or you can put a special e in, either with the palette, you can find it over on the palette, or you can do escape, 2 e's, and another escape to get the number e in there. You can see it looks kind of special. I should probably make that bigger. There it is. And once again, see 1,000 decimal places of e. There we go. E is a little deceiving. It starts out looking like it's going to be a rational number, 2.718281828. Looks like it might be a repeating decimal, but no, after that point it definitely does not repeat the 1828. Alright, it is an irrational number. It's been proven, just like pi is. So e is playing a special role here, evidently. If the interest rate's 100%, then the APY is approaching e minus 1. The b is approaching e. The b is approaching e, actually. What if the interest rate was not 100%? What if it was 50%, which I'll type in as a 1/2? What is the APY, actually the b in this case, approaching? It's not approaching e anymore. It doesn't even look like it's approaching e minus 1. What's it approaching? It's actually approaching e to the 1/2 power, the square root of e. 1.648722127 is what this is approaching. What if the interest rate was 25%, so r was 1/4? Now we're approaching 1.284. That, as you might guess, is e to the 1/4, approximately. What if r was 10%? 1/10. Now we're approaching, as you might guess, e to the 1/10, the 10th root of e, 1.10517. Alright, so e is still playing a special role, really, no matter what r is. That's the main point here. and we're going to explore this role even more in later videos. To end this video, though, I want to think about the compound interest formula as an exponential function. Let me go back to big here. Look at this code. Think about it based on what I've shown you in the past. First of all, we've got a family of functions here. I emphasize that by making the p, r, and n subscripts, though. I actually don't have to do that, but that's the way I like to do it. They do have underscores after them, which does emphasize that in terms of Mathematica's way of viewing them, p, r, and n are variables. But t is the true independent variable for this function. I'm plotting this function as a function of t. It's a family of functions. P, r, and n are the parameters for that family of functions. Different values of p, r, and n will give you different graphs. So I'm plotting all those graphs for different values of p, r, and n. I'm going to make them red. I'm doing the grid lines thing to put the grid lines in there using the table command. If you forgot what the table command does, I can show you here. 0.5i as I goes from 1 to 40. That's going to first give you a value of 0.5, then 1, then 1.5, then 2, then 2.5, then 3, up to 0.5 times 40, up to 20, and put those numbers in a list. And that's specifying that I want the t coordinates of grid lines to be at those values. And for the a coordinates, they're going to be 100 times I. The a value is the accumulated balance. That's going to be higher. The plot range is going to go from 0 to 5,000. I'm going to make the axes thick. P, R, and N are animation parameters. So let's see how it looks when I enter this. There we go. The accumulated balance is a function of time. It's an exponential function, exponential growth. It's increasing and concave up. P is the initial value. It starts out at 1,000. If I change the value of P, that's going to change the initial value of A at time 0. Alright, it's not a vertical translation, it's really a vertical stretch. If you think about the formula, it kind of looks like a translation, but it's not. R is the nominal annual interest rate. Hopefully you can guess that if I increase R, that's going to make the graph, in a sense, more concave up, more and more concave up as R gets bigger and bigger. And if R is small, then you hardly get much exponential growth at all, but it is still technically concave up. You can't really tell, though. N is the number of compounding periods. It doesn't have a huge effect on the graph. In fact, you don't really see any change at all. If I make R bigger, we'll see some change. Okay, let's go back to a small value of n. Watch when I change n. I'm about to do it. You will see the graph change, but it's a slight effect, and as n gets bigger and bigger, you don't see the effect anymore, even though it is still a slight effect. It's the smaller value of n, values of n that give you the bigger effect. But it is not much of an effect. Okay? I'll let you look at the code to end the video.